This is how you solve a 3 by 3 magic square with the numbers 1 to 9. First, write down the numbers 1 to 9 consecutively. Now, when you look at those numbers consecutively, you can see that there are already some of the numbers arranged in a way that add up to 15, which is 5, the center number, multiplied by 3. Those sums are the following. So in 4 different directions, you have the number 15 already. But in the following directions, that form a square, you do not. So what do you do? What you do is you take the odd numbers and you form a symmetrical cross with them. I like to start from the top and I like to move from left to right until you reach the last number at the bottom. Then you take the even numbers and start from the bottom right and create a Z or snake pattern moving upwards, moving in the opposite directions. If the odd numbers you move from left to right, you move from right to left. And you have the solution for the magic square. All these sums add up to 15. In all directions. Now let's analyze what happened, apart from the system that I showed you. What happened is that the number 1 was here, and it rotated 45 degrees. The number 9 was here, and it rotated together with the number 1 45 degrees. Similarly, the number 3 was on the opposite side, and it moved clockwise 45 degrees, but then it was mirrored on the horizontal axis with the number 7. The number 2 was here. Now if we rotate clockwise, it would have come up here. But instead, we mirror it vertically with the number 6 down here. The number 6 was here. So basically, you're rotating and mirroring some of those numbers as well. That is another way of seeing it. I prefer it to the chess move explanation. Now, what's important to notice as well is that the other permutations of this are still the same combination. So there is only one solution to a 3 by 3 magic square with the numbers 1 to 9. And I'll show you why. This has 4 sides. So if I rotate this and I rearrange the numbers so that they are on this plane, I have another solution. If I rotate it again, I have another solution. I just have to rearrange the plane on which the numbers, I have to turn the numbers in this case upside down. If I turn it again, I have another solution. If I turn it one more time, I am back to square one. Also, if I put those numbers in front of a mirror, then again I can rotate. I put them in front of a mirror. All I have to do is turn the numbers on each side around, but I have to turn all of them. The center number remains in the center. And I still have a magic square solution. And I can turn it another 3 times because the square has 4 sides. And I have in all 8 permutations of the exact same solution. What else? Now comes the interesting part, so to speak, when it comes to magic squares. If I take this cross and snake pattern, where the cross is the odd numbers in this case, because we chose the numbers 1 to 9, so we started with the number 1. And the snake is the even numbers. And if I start from the top to bottom, then the even numbers I start from the bottom to top. If I start clockwise with the odd numbers, I move anti-clockwise, or from right to left with the even numbers. You can take this pattern and use it more than once or recursively to solve 3 to the n magic squares. So what does 3 to the n mean? 3 to the n means that instead of just solving a 3 by 3 magic square, which would be 3 by 3, where n is 1, you can solve a larger magic square where n is 2, for example. So it will be a 9 by 9 magic square. Now, even just to draw the 9 by 9 magic square, we can either draw it line by line, or we can draw it in a nested way, and that is exactly how the solution shows itself. So I did a 3 by 3 grid, and in each one of the squares I can put another 3 by 3 grid. So geometrically, like this, we get insight on the numerical solution. Now, this doesn't just work for consecutive numbers, it works for any set of numbers that has a particular order. So the center is here. The center remains where it was. So first you have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. It's a bit pedantic. 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 40. Oh wait, 41 is here. 41, 42, 43, 44, 45, 46, 47, 48, 9, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, and 81. So, in a 9 by 9 magic square grid with consecutive numbers starting from 1 and ending to 81, those are the numbers. Now, what do I mean when you can use the same pattern we used in the 3 by 3 grid to solve this one? This is not the only solution, but it is quite an efficient and reliable solution. So just like we nested trees inside each part of a 3 by 3, we can do the same thing with the numbers. What we do is we take a slice and we do it 9 times of each 3 by 3 grid, part of the grid of the 9 by 9. So here, the first slice would be in the top left corner, where there are the numbers 1, 2, 3, 10, 11, 12, 19, 20, and 21. These are not consecutive numbers, but they do indeed have a pattern. And the pattern is quite simple. The pattern is that moving down each row, we have the same numbers we have in the first row, but we are adding nine each time. So if the first 3 numbers are A, B, and C, underneath we are adding, underneath we have A again, but plus a constant n, B plus a constant n, and C plus a constant n. In this case, A, B, and C are the numbers 1, 2, 3. And the constant n is 9, obviously. But let's explain it, because there are 9 columns, so the last number in the first column is 9, so the next number is 10. So there is a difference of 9 each time. Horizontally, there is only a difference of 1, but vertically, there is a difference of 9. And that is enough for those numbers to be consecutive enough to add up to a magic square. So if we take this first slice here and we resolve it, all we have to do is to consider the position of those numbers. and pretend that they are the numbers 1 to 9. So first we have 1, 2, 3, then we have 10, 11, 12 instead of 4, 5, and 6, and then instead of 7, 8, and 9 we have 19, 20, and 21. So that solution would be as follows. So, instead of the odd numbers 1, 3, 5, 7, and 9, we have 1, 3, 11, 19, and 21, because we use the same pattern. Instead of considering the numbers, we're considering the positions of those numbers on the grid. And instead of the numbers 2, 4, 6, and 8, we have the numbers 2, 10, 12, and 20. So that is the first step that we have to do 9 times to solve a 9 by 9 magic square using this method. So we do the same thing for each of the remaining 8 3 by 3 squares in the 9 by 9 grid. And then, so I'm going to use the same example of the first slice. We zoom out. We don't erase the numbers, but we zoom out. This is just for illustration purposes. We zoom out. And again, we consider those 9 numbers in the first part of the grid as if to be a single number, and we demark it by its position. That's the first, where I like to start from left to right and top to bottom, so this is the first position, and the first position would put it as the number 1. Then, since we're doing it for all the other 3 by 3 grids in the 9 by 9, we take this, after arranging it internally, we take this whole result. This is already a magic square, but it's a 3 by 3 magic square. We take all this 3 by 3 magic square that we solved, and we place it where we would have placed the number 1 in the 3 by 3 original grid. So this one here then becomes placed correctly in the 9 by 9 grid. We do the same thing for each of the other 3 by 3 grids. So if we imagine, so this remains empty now because we moved it one step to the left, and all this is the number 1. So, over here, in the original 3 by 3 magic square, was the number 8. So, the number 8 would correspond to this, the 8th block in the sequential grid. So, this is not a magic square yet. This is the numbers in sequence, and we're starting to solve it as a magic square. You take this, all this, right, once you solve it. So let's solve it here. So that's the number 77, 58, 69, 60, 68, 76, 67, 78, 59. So we just considered the position of the first number and we placed it as if it was the number 1. We considered the position of the third number and we placed it as if it was the number 3. It's kind of like a battleship game. So all this then, as I explained already, I'm not going to stay doing all of them, would be, in this case, for convenience, I chose the number 8 because it's already deleted, would be the number 8. And we place it here. So, like that, we used the same pattern of a cross with a snake on its 45-degree rotation, however you want to picture solving a 3x3 magic square. And we used it twice. We used it twice because the 3x3 grid is to the power of 2. So 3 to the n denominates not just the size of the square, but n is also the number of steps. And the steps are the same. You just have to zoom out. So that is how you solve a 9x9 magic square using this method. This method is infinitely recursive. So it never ends. Why is this important? Maybe. This is important not just for convenience sake, because even if you know the pattern, you still have to stay doing all the steps, but it might be useful because if it's infinitely recursive, it might also apply to prime numbers. What do I mean? What I mean is that if the numbers, instead of being consecutive, are all prime, but you have to leave out the number 2 and the number 5. You have to leave out the number 2 because the number 2 is the only prime number that's an even number. And the number 3, I suspect you have to leave it out because it's a multiple of 3. You can, by skipping and not necessarily having there are consecutive magic squares with consecutive primes, but by skipping primes as well, you can create, and I managed to create an 81 by 81 nested magic square. Now I'm hoping that through repetition, like I did for the regular 3 to the n magic squares, that I might find a pattern that relates to primes. And for those who are not aware, primes have been elusive for over 2,000 years. I think for now that is enough. There's more you can say about but I think what I said is enough.